one of our biggest challenges and strengths of the hardware team is to design for efficiency so that we could scale for any car in the world.
Welcome to Talking Autonomy. In this episode, we're going to dive into the world of hardware, and specifically how we design hardware to power all the software-defined functions that deliver autonomy here at Ghost. I'm joined today by Arpita. Welcome.
Hi.
Can you introduce yourself, tell folks what you do here at Ghost, and maybe a little bit of what you did in your career before joining us?
Sure. So right now at Ghost, I work for the hardware-software integration, spend most of my time working, designing hardware, and rest of the time getting software requirements to design the hardware. Before this, I was designing drones with Amazon for their delivery service, autonomous again, and before that, I was making servers, x86 servers for like 5-6 years.
All right. Lots of cool, diverse projects. So you also brought some toys for us to play with, which I'm excited about. So before we check out what's on the table, maybe just give us a real high-level view. How do we think about the hardware philosophy here at Ghost?
So at Ghost, we mostly define hardware, which is basically, or take an approach, which is basically software-defined hardware. So what that means is we design for scale. And designing for scale is mostly that this hardware can fit in any car, whether it be luxury end or the less than luxury end cars, and we can run all different models and software on our hardware.
Yeah, I know the team is super demanding when they ask for, all right, we need a sensor stack that can, make sense in like a $30,000 car as well as a $200,000, SUV.
Yes, and we have to fit all those requirements.
Yeah. Well, and it really changes everything in the company. I mean, when you start with a spec that says this has to go in every car, it begets a certain hardware recipe, and that hardware recipe is co-designed with the software because you need, an approach to the software that can work on this level of hardware. And so it's just inherent in everything that we do to co-design these elements.
Absolutely. And I think the key approach there is to have a more generalized approach to doing hardware. So like an open design, then being like very specific design goal approach. And even though the second one gives you much efficiency, I think having a generalized approach is what has worked for Ghost and has made us very diverse.
Yeah. I mean, I feel like this is a bit of a trend in the auto industry where the old approach was to have tons of ECUs all around the car, kind of a specific processor, sometimes an FPGA, sometimes a dedicated ASIC, for a bunch of different functions. And then, what you're now seeing is a centralization and a realization that if we use central compute and do things in software, you can be much more flexible, adapt quickly, et cetera.
Exactly. And for that, we also we have to give up this whole being exclusive and doing one certain goal when we design hardware, and we have to be applicable to all different technologies. So our hardware can adapt to every different thing our amazing software team comes up with. So
I imagine that occasionally the software team comes up with a new approach to something, and they just, has to kind of work on the hardware. So
we just have to provide enough compute for them to do that and have enough flexibility on our boards. So.
Yeah, makes sense. So let's dive into looking a little bit at some of the stuff you brought here on the table.
Absolutely.
I think one of the other unique approaches at Ghost is that we really try to build hardware in a way that it could be something that goes in a real production car.
Right.
And so oftentimes when you look at autonomous projects, you see all kinds of sensors strapped to the outside of the car. You see a trunk full of PC tower computers, extra power, all
cooling
that.
Systems.
Cooling systems,
Yep.
You name it. And in our case, this is basically what you can drive off of what you see on the table here.
And all of this comes under 1,500, and or that's the market price we're aiming towards, and everything under 150 watts. And I think we have successfully accomplished that, and we are pretty proud of it.
Yeah, I mean those are incredible stats. If you look at kind of the gear that might go in, let's just say a robo-taxi, it's probably not uncommon to see $30,000 or $50,000 worth of compute, sensors, hardware strapped to one of those devices. We're trying to do this in under $1,500 just for the hardware at kind of production scale and 150 watts. And I mean, in our cars today, we just run off the standard alternator, right?
Yeah, right.
Exactly. All right, so let's check this out. So first of all, this is the compute unit, right?
Correct. This is what we are driving off in our cars right now. So basically what you see is this board here that's inside. We have a battery system here inside as well to help us in situations when we are not drawing power from the car. And yeah, so each of them have, if you would like to.
I mean, not to date myself, but this kind of looks like a CD changer that might have gone in my car in the 80s.
Absolutely,
Yes.
absolutely. This is cooled by just generic fans as well, and it's under 100 watts.
Under 100 watts for
Yep.
the compute complex. And
Yep.
so this is the board.
Yep.
I see 5 processors on there.
Yeah. So there are 5 processors, and there's like flexibility for CAN transceivers that we connect to the car. Here's a little micro that does all the power monitoring for this and the sequencing for this. But yeah, we basically are running the car on highways based on these 5 SoCs.
Yeah, the processor is a Qualcomm 845. I mean, this is literally like a 6 or 7-year-old cell phone processor, right? It's like the size of my thumbnail here,
Yeah,
or smaller.
and it's like 7 to 8 watts each, or even less than that.
Wow.
And this also has the flexibility to connect to cameras. And as you have the cameras here,
Speaking of which, yeah. So this is the camera module.
this is our 12 megapixel cameras. Like you said, this is our mobile system cameras. So we have designed for pooling this in the car. And so you see here, it's basically, so going by our scalable design, this is just a flex MIPI connection coming out from the cameras. And you can plug it to any compute the way you've designed it, and it's not dependent on what you have on the other end.
Well, and I mean, essentially that has a bit of a longer lens on it because we're looking far, but that's essentially equivalent to the camera I might find in my cell phone, right?
Absolutely.
Yeah.
Yep.
Since we're talking cameras, why don't you explain what this guy is?
So this is our next gen cameras. So like I said, those were our infotainment, or more of the camera that you find in your phone. This is our automotive grade camera. An automotive grade camera has to withstand higher automotive temperatures. So this does that. And not only that, this also has all the electronics built into it. So like all the serializing is done inside this. So it's pretty tiny for that.
Nice.
And yeah, so then you just have like one coax cable connected to your compute. And right now we have about like 8 cameras on a car.
Yeah, have
4 pairs, that's
stereo in every direction. All right, and then this is our front window module, right?
Right. So basically, this is our front camera assembly, which basically has this first camera that I showed you, a stereo of them, and then it has this interior camera inside for monitoring driver intent. Yeah, so this is the board that fits very nicely.
Kind of goes like this on the window, and you see the 2
and
cameras coming out.
And it takes the profile of the windshield. Looks pretty neat.
Nice. Yeah, and so essentially this will give us, what is that, 17 centimeters of disparity between the 2 cameras?
Yeah, 70.1.
Nice. All right. So thanks for showing us all the hardware. Let's loop back around and talk a little bit more about the whole software-defined design. Now, in the past, as we said, the common approach was lots of pieces spread around the car. And if you look, for example, at say a camera or radar, you would typically have a camera, a radar, and then maybe a chip right next to it to process its raw data. And then just small amounts of highly processed data were sent to the centralized, driving ECU. And so we've turned that wholly upside down, right? So how is the new design architected?
So I think the key decision behind that is to offer flexibility again. So when we have like raw data, our neural net can like process the way it wants to, run different kinds of models, and that gives us flexibility, and we're not tied down to whatever we get from the upstream. The initial bottleneck was probably like, and that would be a challenge in even any industry, is like compute compared to efficiency of power, right? And I think once you nail that down, and you can probably provide enough compute power without using too much power, I think the best decision is to get all the raw inputs and do your modeling in the big compute system, and have one master or one master computer. Okay. So that's the approach that we do here as well.
Yeah, I mean, it does seem like it provides the ultimate flexibility, and just the notion that if I bake something into an ASIC that's going to be in a car for 10 years, it can never be changed. Right. And so no one wants to run off a neural network from a decade ago in their car.
And also, like, that also makes these peripheral sensors like easy to service and like cheap and more affordable or more scalable than having like individual ASICs for each of them in assemblies or.
Yeah, I mean, I think the other thing that I've heard a lot from the automakers recently after the last few years is supply chain. That they got in a situation where one little ASIC on one little function stopped an entire production line because they couldn't get a hold of it.
Right, and these have to work for 10 years. That's the whole definition of automotive, right?
Yep, exactly. Okay. So the last piece, as you see here, we built, production-ready hardware. It's something that could literally go in a car. But obviously, since we don't design the car, we can't do the perfect integration where the camera might be in the B pillar or the front camera might be integrated in the same, assembly as the rear view mirror. And so, how do we work with automakers to take this design, to them?
So our approach here is to provide them with blueprints, model the idea, do a proof of concept, and show them how it's done. And I think from the blueprint, they can choose how to customize things according to their fit and where to, say, install things, change form factors. But the basic concept comes from us.
Yeah, and so our goal is to provide kind of a reference architecture, but
Correct.
They're the experts at large scale manufacturing, design for auto grade, testing out to
Exactly.
all those extreme use cases, et cetera.
Especially a lot of automotive electronics also has to go through compliance testing and automotive standards, and automakers have been doing that for years with their electronics in their system, and hence they scale power and battery and everything accordingly. So it's the perfect fit too.
All right. Well, Arpita, thanks so much for giving this small window into the Ghost hardware, and we'll look forward to. This is just our first generation hardware. We're actually in the transition period right now, where a whole new hardware architecture is coming out. You can see the camera there, but there's a lot more coming. So, look forward to talking with you about that shortly when that is available.
Thank you. Thank you for having me here.